Not all distances can be measured easily by physical means. However, using the techniques of integration, we can find the length of any smooth curve for which there is a continuous function. Hi, my name is Tom Atwater, and that's what we'll be delving into in today's lesson. There are two properties of functions that are important to the general formula for the length of a smooth curve. The curve must be differentiable, and its first derivative must be continuous. And this is called smoothness. A function with a continuous derivative is called a smooth function, and its graph is called a smooth curve. Now we can look at the formula for the arc length. If a smooth curve begins at A comma C and ends at B comma D, such that A is less than B and C is less than D, then the length, as arc length, of the curve is given by the formula L equals the integral from A to B of the square root of the quantity 1 plus dy dx squared dx. If y is a smooth function of x on the closed interval AB, and the arc length is equal to the integral from C to D of the square root of the quantity 1 plus dx dy squared times dy, if x is a smooth function of y on the closed interval C comma D. Let's look at an example where we can apply this formula. Find the exact length of the curve analytically by anti-differentiation. You will need to simplify the integrand algebraically before finding an antiderivative. Y equals 1/3 of the quantity x squared plus 2 raised to the power 3/2 from x equals 0 to x equals 3. So the first thing we need to do is find the derivative dy dx. So let's do that. Dy dx would be equal to, I pull down the 3/2 multiplied by the 1/3, take the x squared plus 2, raise that now to the 1/2, and then using the chain rule with the x squared, multiply by 2x. This cleans up actually quite nicely. Our 2's cancel to 1, our 3's cancel to 1, and so we end up with x times x squared plus 2 raised to the 1/2. So now we can plug this into the arc length formula since we have our dy dx. And the arc length formula is L equals the integral, and in this case it's from 0 to 3, of the square root of 1 plus dy dx squared, so it's x times x squared plus 2 raised to the 1/2, and then that is squared. And of course, it's with respect to x. So this is going to equal the integral from 0 to 3, and we have to apply the power of 2 to each of these factors, so that what we get is the square root of 1 plus x squared times x squared plus 2, and of course the 1/2 and the 2 cancel to 1. So when I simplify all of this, it simplifies quite nicely because this is x to the 4th plus 2x squared plus 1, which is just the binomial x squared plus 1 squared dx. Okay, so what I want to point out is over here we have the square root of x squared plus 1 squared, i.e. the square root of the squared will cancel each other out, leaving us with, and I need some space, so I'm going to erase a little bit here and bring my problem up into this area. What I have is going to be the integral from 0 to 3 of the absolute value of x squared plus 1 dx, which I can evaluate in terms of x cubed over 3 plus x evaluated from 0 to 3. And notice that I've dropped the absolute value bars because the absolute value bars require this to be positive. But on the interval from 0 to 3, x cubed over 3 plus x is positive. So we don't need the absolute value bars. And when I plug everything in and simplify it, I'll get my arc length is equal to 12. All right, great. Sometimes a curve has a vertical tangent, corner, or cusp, where the derivative that we need to work with is undefined. We can sometimes get around such a difficulty in a way that I'm about to illustrate in the following example. Find the length of the curve y equals the cube root of x between -8, -2 and 8, 2. Now, this does have a difficulty, which we can see if we graph y equals the cube root of x, which passes through the origin. And the difficulty is that as we look at the slopes of the tangent lines, as we get close to 0, at 0, the tangent line is completely vertical, which gives us an undefined slope, which means our derivative of y with respect to x at that particular point is undefined. However, if we rewrite the problem, x equals y cubed, then what we're looking at is a function which now, instead of having a vertical tangent, will have a horizontal tangent at 0. And a horizontal tangent means that the derivative is 0. So now we actually have a derivative at the point of x equals 0. And we can therefore use the second of the two formulas for arc length, because what we'll do now is take the derivative of x with respect to y. So dx dy is going to be equal to 3y squared. So we can use this in the formula, and let's set up our integral for the arc length now. We would have the arc length of the square root of 1 plus, and this time it is dx dy 3y squared dy, and the limits of integration that we're dealing with are from -2 to +2. We can put that into our n int, and when we do this, we will come up with an answer equaling 17.26. And that would be the arc length for that particular curve. Now let's look at a problem that includes a corner. We have find the length of the curve y equals x squared minus 4 times the absolute value of x minus x from x equals -4 to 4. Let me show you a graph of that curve. And you can see clearly that we have a corner right at x equaling 0. And therefore, what we're going to do in order to get by this difficulty is we're going to split this up. Anytime there is an absolute value, we must always be on the lookout for something like an abrupt change in the slope. And you can see by graphing it that we see a corner right at x equals 0 where, remember, neither the derivative with respect to x or the derivative with respect to y, that is, neither of the derivatives will exist at that point. So we have a difficulty there. The way that we'll get it is to split the curve at x equals 0. And we'll write the function as two separate functions, and we will use the arc length formula for each half, adding them together. So let's do that. What we would have is that x squared minus 4 absolute values of x minus 1 is equal to x squared plus 3x if x is less than 0. And that it's equal to x squared minus 5x if x is greater than or equal to 0. So now we have to find the derivative of each of those. So the derivative of x squared plus 3x would be equal to 2x plus 3. The derivative of x squared minus 5x, dy dx, would be equal to 2x minus 5. And so when we set up our integrals, we would have the integral from negative 4 to 0, which is when x, of course, is negative, and that would be the square root of 1 plus 2x plus 3 squared dx. And then we have to add to that our other integral, which starts at 0 and goes to 4. And that would be the square root of 1 plus 2x minus 5 squared dx. Again, let's put that into an int. And when we do that, we will get our answer of 19.56 as the arc length of that curve that involves the absolute value. Well, we handle cusps in the same way as we did the corners. We split the curve into smooth pieces and then add the lengths of those pieces. Well, now it's time for you to try a problem. I want you to find the length of the curve y equals x cubed plus 5 absolute value of x from x equals negative 2 to x equals 1. Pause the video while you work on this problem, and when you are finished, restart the video to check your solution. Well, I hope that you either put that formula into your graphing calculator and graphed it, or at least drew a sketch so you would see that there is a corner right at x equals 0. And therefore, as I did in the previous example, we would have to split that function into two different functions and then integrate each separate function on its interval and add those together to get our arc length. So let's take a look at what that would be. We would have that x cubed plus 5 absolute value of x is equal to, we would get x cubed plus 5x if x is greater than or equal to 0. And we would get x cubed minus 5x if x is less than 0. We need to find the derivative of each of these. So I'm going to do it right underneath here, but I'll do it in blue just to offset it. So we'd have 3x squared plus 5. And for my other derivative, I would have 3x squared minus 5. So now I can set up my integral, which would be the integral from -2 up to 0 of the square root of 1 plus 3x squared minus 5 squared dx, plus the integral from 0 to 1 of the square root of 1 plus 3x squared plus 5 squared dx. Again, using the calculator and using n int, we would get an answer equal to 13.132. I hope that's the answer you got when you worked out the problem for the arc length. Great job in today's session. So today we explored arc length with the difficulties of a vertical tangent, a corner, and a cusp, and how to handle when those situations arise. Be sure to work the exercises that your teacher assigns, and we'll see you next time.